On June 1, 2009, Air France Flight 447 departed Rio de Janeiro for Paris, a routine overnight journey across the Atlantic. A modern Airbus A330, packed with sophisticated technology and a seasoned crew, it represented the pinnacle of contemporary air travel. Yet, somewhere over the vast, dark ocean, this advanced airliner simply vanished. No distress call, no clear indication of trouble, just an abrupt cessation of communication, leaving behind a profound mystery and a desperate, agonizing search. The world watched, baffled by the disappearance of such a technologically advanced aircraft. AF-447, an Airbus A330-203, was a workhorse of long-haul aviation. Its route over the Atlantic was well established, crossing through the Intertropical Convergence Zone, or ITCZ, a region known for severe thunderstorms and high-altitude ice crystals. Pilots were accustomed to navigating this unpredictable weather, often making minor detours to avoid the worst of it. The aircraft itself was highly automated, designed to fly with minimal direct human input for much of its journey, a testament to modern aerospace engineering and efficiency, offering comfort and safety to its passengers. At the heart of any aircraft operation, especially an automated one, is accurate airspeed data. This vital information is primarily gathered by small, external sensors known as pitot tubes. These tubes, typically mounted on the fuselage or wings, are deceptively simple in appearance but critical in function. They measure dynamic pressure, which is then translated into the aircraft's indicated airspeed. Without reliable airspeed data, the flight control computers cannot operate effectively, and the autopilot, which relies heavily on this input, becomes blind, unable to maintain stable flight parameters. As AF-447 progressed into the ITCZ, it encountered the expected severe weather. Towering cumulonimbus clouds, characteristic of the region, rose to extreme altitudes, harboring intense updrafts, turbulence, and significant concentrations of supercooled water droplets and high-altitude ice crystals. The crew, aware of the conditions, attempted to navigate around the most intense cells. However, the sheer scale of the weather system meant that avoiding all areas of potential hazard was simply not possible. The aircraft was heading directly towards a confrontation with nature's raw power. At approximately 2:10 Universal Time Coordinated, the crucial moment arrived. The aircraft, flying at 35,000 feet, entered a region with significant ice crystals. These tiny particles, invisible to radar, began to ingress and block the aircraft's pitot tubes. This was the single system's fatal flaw. The blockage meant that the pitot tubes could no longer accurately measure the dynamic pressure, instantly corrupting the airspeed data. The aircraft's highly integrated systems, dependent on this fundamental input, suddenly faced an existential crisis. The reliable flow of information was severed, silently and without immediate warning. With the airspeed data compromised, the aircraft's advanced automation reacted swiftly and decisively. The autopilot, unable to receive the critical information it needed to maintain controlled flight, automatically disengaged. Almost simultaneously, the auto-thrust system, which manages engine power, also deactivated. These actions were designed as a failsafe, returning control to the human pilots when the automation could no longer guarantee safety. However, for the crew, this meant an abrupt transition from a highly automated, stable cruise to manual flight in turbulent weather, compounded by unreliable primary flight data. The cockpit was plunged into a state of confusion. The loss of airspeed data triggered an unreliable airspeed warning, accompanied by the master caution. However, the situation was dynamic. As the ice briefly cleared, airspeed indications flickered back to life, only to disappear again. The crew was presented with contradictory information: valid airspeed from one source, zero airspeed from another, and warnings that came and went. In a high-stress environment, this unreliable data created a profound challenge, making it incredibly difficult to accurately assess the aircraft's state and determine the correct course of action. In the chaos that ensued, the first officer, the pilot flying at the time, made a critical input, a sustained stickback command. This action, held for approximately 30 seconds, commanded the aircraft to pitch up, increasing its angle of attack and decreasing airspeed. It's a natural reaction for some pilots during a loss of airspeed indication, often to prevent an overspeed, but in this specific scenario, without reliable data, it was precisely the wrong response. Unbeknownst to the crew, this input was rapidly pushing the aircraft towards an aerodynamic stall, a condition from which recovery would prove impossible. As the aircraft's angle of attack continued to rise due to the stickback input, the stall warning system activated. This audible alarm and visual indication is designed to alert pilots that the wings are losing lift and an aerodynamic stall is imminent. However, here again, the unreliable airspeed data created confusion. The stall warning intermittently activated and then silenced as the airspeed indications fluctuated. This on-again, off-again nature of the warning likely diluted its urgency for the crew, contributing to their inability to fully grasp the dire situation developing around them. Despite the stall warnings and the high-pitch attitude, the crew seemingly did not recognize that the aircraft was in an aerodynamic stall. The lack of specific training for an unreliable airspeed scenario at high altitude, coupled with the contradictory data and the automation's disengagement, meant they lacked the mental model to accurately diagnose the situation. Instead of pushing the nose down to gain speed and recover from the stall, the stickback input continued, exacerbating the problem. The pilots were fighting an invisible enemy, unable to reconcile the instruments with their own perceptions. From its cruising altitude of 35,000 feet, Air France for 47 began an uncontrolled descent. That stickback input, maintained for much of the incident, kept the aircraft in a stalled configuration. It fell, nose high, losing altitude at an alarming rate of up to 10,000 feet per minute. The stall warning, now consistent, blared through the cockpit, a final desperate plea from the aircraft. But with the crew still unable to implement the correct recovery actions, the fate of the flight was sealed. The single system's initial failure had snowballed into an irrecoverable freefall. After approximately 3 minutes and 30 seconds in a stalled descent, Air France flight for 47 impacted the surface of the Atlantic Ocean. The aircraft hit the water virtually flat, at an extremely high vertical speed, leading to its complete disintegration. There was no chance of survival for any of the 228 people on board. The vastness of the ocean quickly swallowed the debris, leaving only a scattering of wreckage to be found later. This catastrophic conclusion underscored the immense power of a single system's failure, setting in motion an irreversible sequence of events. The immediate aftermath was dominated by a painstaking and challenging search and recovery operation across hundreds of square miles of open ocean. For weeks, rescue teams scoured the surface for any signs of the aircraft or its passengers. The discovery of debris, including parts of the tail fin and bodies, confirmed the worst but offered few clues as to why. To truly understand the disaster, investigators needed the black boxes, the flight data recorder, FDR, and cockpit voice recorder, CVR, which lay thousands of meters beneath the ocean's surface, a formidable challenge to locate. It took nearly 2 years, multiple search phases, and unprecedented deep-sea recovery efforts to finally locate and retrieve the black boxes in May 2011. Their data proved invaluable. The flight data recorder confirmed the initial loss of airspeed data due to Pitot tube icing. The cockpit voice recorder laid bare the crew's confusion, their struggle to understand the warnings, and the critical stickback input that ultimately led to the stall. The evidence was undeniable. The single system's failure initiated a sequence that exposed the limitations of both automation and human training. The final report by France's Bureau of Inquiry and Analysis for Civil Aviation Safety, BA, meticulously detailed the sequence of events. It confirmed that the blockage of the Pitot tubes by ice crystals was the initiating factor. This led to the loss of reliable airspeed data, which in turn caused the autopilot and autothrust to disconnect. The crew's subsequent actions, primarily the sustained nose-up input, maintained the aircraft in an aerodynamic stall from which they failed to recover. It was a complex interaction, but the single system's failure was undeniably the linchpin of the entire tragedy. Crucially, the Pitot tube icing was not an entirely unknown phenomenon. There had been previous, less severe incidents where Airbus aircraft experienced temporary loss of airspeed data due to ice crystals, particularly with the Thales model Pitot tubes installed on AF-47. While manufacturers had begun testing new designs, the full scope of the vulnerability and its potential to trigger such a catastrophic chain of events was not fully appreciated until AF-47. This incident laid bare a systemic weakness in a critical flight system, challenging previously held assumptions about its robustness. The AF-47 disaster also highlighted the paradox of advanced automation in modern airliners. While automation significantly enhances safety and efficiency for most flights, it can sometimes degrade a pilot's fundamental manual flying skills. When automation abruptly disengages, especially in an emergency with unreliable data, pilots must immediately take full control and diagnose complex situations. The crew of AF-47, highly skilled in automated flight, struggled with the transition to manual flight under extreme stress and a critical system failure, emphasizing the need for adaptable pilot capabilities. The investigation revealed significant gaps in pilot training for high-altitude unreliable airspeed scenarios, particularly concerning how to correctly manage a pitch-up attitude and recover from a stall. While pilots were trained for stall recovery at lower altitudes, the specifics of a high-altitude stall, coupled with conflicting data, were not adequately covered. The crew's repeated stick-back inputs, despite stall warnings, indicated a fundamental misunderstanding of the aircraft state. The human factor, reacting to the single system's failure, became a critical component in the unfolding tragedy. In response to the AF-47 accident, a swift and decisive action was taken by the aviation industry. Pitot tube manufacturers, primarily Thales and Goodrich, accelerated the development and deployment of new, more robust designs. These improved Pitot tubes were engineered to be more resilient against ice crystal blockage, often incorporating enhanced heating elements or redesigned geometries. Airlines worldwide were mandated to replace the older, less reliable Pitot tubes on their Airbus fleets. This direct intervention targeted the single system that initiated the entire chain of events, aiming to prevent a recurrence. Beyond hardware changes, aviation authorities and airlines globally overhauled pilot training programs. A new emphasis was placed on manual flying skills, particularly in managing unreliable airspeed scenarios and high-altitude stalls. Pilots now undergo rigorous simulator training to practice these critical procedures, learning to differentiate between valid and invalid data, and to prioritize fundamental flight principles over potentially misleading instrument readings. The goal is to ensure pilots are better equipped to handle complex emergencies when automation, due to a single system's failure, is no longer available to assist them. The tragedy of Air France Flight 447, initiated by the failure of a single system, the Pitot tubes, left an indelible mark on aviation. It spurred a re-evaluation of how aircraft are designed, how pilots are trained, and how automated systems interact with human operators. While no single factor directly causes an accident, the Pitot tube icing was the critical trigger that unleashed a cascade of events, exposing vulnerabilities previously underestimated. The lessons learned from AF-47 continue to shape flight safety, reminding us that even the smallest component can have monumental consequences in complex systems. The story of AF-47 is a stark reminder that modern aviation, despite its marvels, remains a complex interplay of technology and human factors. While the Pitot tubes were the initial point of failure, the disaster ultimately involved the aircraft's automated responses, the crew's interpretations of conflicting data, and the limitations of existing training. It underscores that understanding how a single system's failure can propagate through an entire network of highly integrated components is crucial. Every design, every protocol, every training module must account for these potential domino effects. From the profound darkness of the Atlantic, Air France Flight 447 delivered crucial, albeit tragic, lessons. It served as a powerful testament to the fact that even the most robust and advanced systems can be brought down by a vulnerability in a single, fundamental component. The commitment to understanding and mitigating such risks is ceaseless. Every flight that takes off today, every pilot who undergoes training, every design improvement implemented, carries with it the enduring legacy of AF for 47, ensuring that the vigilance against even the smallest potential point of failure remains paramount.